Right now, satellites in low Earth orbit are beaming shared quantum states through the vacuum of space, actively networking ground stations separated by hundreds of miles. Classical networking routes physical bits of data, discrete ones and zeros traveling along fiber optic cables. Quantum networking, by contrast, focuses on the distribution of shared quantum states. In formal terms, entanglement is a condition where two or more particles form an inseparable compound wave function. This system cannot be factored into the product of its local constituents. This is the mathematical representation of the maximally entangled Bell state. This equation shows a simultaneous superposition of outcomes. The state exists as a probability distribution of these combined results, rather than a single fixed value. Under this unified system, the particles no longer possess individual identities. They remain a single entity regardless of the physical distance separating them. Physics once treated this behavior as a philosophical anomaly. Today, we quantify it as an active engineering resource. Trace the development of this resource from the micromechanics of quantum logic gates to the macro-scale architecture of satellite distribution. Mastering this non-local physical phenomenon is the prerequisite for building high-speed multi-party computation and the communication protocols of the next decade. We begin with two independent qubits initialized in the zero state. Applying a Hadamard gate branches the first into dual probability waves. A controlled NOT gate then merges these separate waves into a single interlocking vector. To test the limits of this joint state, imagine the newly synthesized entangled pair physically separated by a vast distance. Prior to measurement, neither particle has a definite local state. They exist only as the shared probabilities mapped by the wave function. When one particle is measured, it is forced into a definite state, which instantly collapses the entire shared wave function. The distant partner instantaneously assumes the corresponding state required by the mathematics of the Bell state, regardless of spatial distance. This non-local collapse is a mechanically synthesized reality built from standard logic gates. In 1935, Einstein, Podolsky, and Rosen published a formal objection to this mathematics, questioning the completeness of quantum mechanics. Einstein argued for local realism, which requires the universe to possess separability, where objects have independent states, and locality, where influences cannot exceed the speed of light. Einstein rejected the idea of instantaneous collapse, famously characterizing it as spooky action at a distance. He proposed hidden variables, the idea that particles carry pre-programmed instructions from the moment of creation, much like a pair of separated gloves. This disagreement traces back to the 1927 Solvay Conference, marking the start of a multi-decade debate between Einstein and Niels Bohr. In 1964, John Bell introduced a mathematical framework to test these local hidden variables against quantum mechanics empirically. Bell's theorem provided the method to prove that the correlations observed in entangled particles cannot be explained by any local hidden variable theory. Subsequent physical experiments confirmed the violation of Bell's inequalities, supporting the non-local predictions of the quantum model. These results require us to move past classical intuition. Non-local wave function collapse is a verified physical law. If collapse is truly instantaneous, we must ask why it does not violate special relativity or permit faster-than-light communication. The answer lies in the probabilistic nature of measurement. Alice cannot choose her outcome to encode a deliberate message. Her result is fundamentally random. Because of this, Bob's instantaneous correlation appears equally random, yielding no recognizable pattern without more data. The no communication theorem states that extracting usable information from these correlations requires a classical communication channel. Alice must transmit her specific measurement results to Bob via conventional means, which remains strictly limited by the speed of light. Bob applies those classical bits to perform a local operation on his qubit, a step that allows him to recover the intended quantum state. Entanglement preserves the causal geometry of spacetime. Special relativity remains unbroken, even though the quantum linkage is absolute. Shifting from foundational physics to application, entanglement serves as the core engine for quantum advantage. While classical bits scale linearly, entangled qubits scale exponentially, weaving together to process massive amounts of data in parallel. This connectivity opens up a massive Hilbert space, the multidimensional computational area representing all possible states in the system. Entanglement is the physical mechanism that allows a processor to navigate this vast probability space simultaneously. However, these systems are vulnerable to decoherence. If environmental interaction breaks the coherence, the entanglement fails, and the quantum processor collapses into an inefficient classical simulator. Establishing long-distance entanglement and maintaining coherence are the primary technical barriers to achieving a practical quantum advantage. The challenge now is scaling this resource beyond isolated labs to build a global network. Photons traveling through terrestrial fiber optic cables experience absorption and scattering. This limits entanglement distribution to roughly 100 kilometers without intervention. Low Earth orbit satellites, such as the Messias mission, provide the engineering solution to bypass these terrestrial limits. Transmitting photons through the near vacuum of space drastically reduces scattering and signal loss compared to terrestrial fiber networks. The Messias mission demonstrated this by distributing entangled pairs between ground stations separated by 1,200 kilometers. Scaling this into a global network requires a protocol known as entanglement swagging. In this process, a relay node performs a joint measurement on two separate entangled pairs. This instantly links the distant partners, even though they never interacted. This framework chains nodes together, connecting cities and continents through quantum relays. The non-local correlations Einstein once questioned are now being deployed as a functional utility, linking orbital and terrestrial nodes into a high-capacity